for themselves. So, okay. Right. Okay. So after the reconstruction itself, what you can get is the 3D features. And together with the all the software, all the fancy software today, you can study all the properties by looking at the 3D. You can look at the porosity out of the certain volume. You can look at the density out of the certain volume. So it can give you very accurate measurements and a lot of information out of the 3D features of it. And what you can see here is what we call it as a slice. So you have do the scanning, the CT scanning, and then after it has reconstructed, what you can see from the software itself is the slices. So you will not see the 3D yet until you have done the reconstruction all merged together and you get the 3D again. So mhm.
Okay there.
Yep, yep, my wait. Mhm. Wait, something wrong. Cannot move to the next slide. Okay, okay, back to normal. So this is what you can see is image, a slice of an image out of a clinical CT scan. So because of fast scanning as well as to expose a very low radiation to the patient, you will see the resolution is slightly poorer and the resolution for hospital grade or clinical grade of CT is mainly ranges from like about 100 micron up to in like level. However, their focus is to have a good contrast, signal over noise ratio, good contrast, especially on the soft tissue, as well as the low radiation exposure. So compared to ex vivo, or what we call it as a MicroCT, especially for non-living type of samples, it normally come with a very good resolution. So up to like submicron, even up to a submicron level of a resolution, like what you can see here. So the principle of MicroCT is very straightforward. So what it is depending on is the coefficient, the attenuation coefficient. So you can see based on this law, Beer-Lambert law, and depends to the materials and the density of this and the homogeneity of the material. So like what you can see here, we have a bone, this is a muscle, this is fat. So this is indicating the attenuation coefficient, and this is indicating the level of the kV. So the higher the kV, you will see the differences between the attenuation coefficient is smaller. So which means that if you utilize a high kV, you will be expecting less contrast in between these three types of material. So if your focus is on bone or tooth, it's very straightforward. You just need to use like 7 kV and above. So it will give you nice images. But if you're looking at fat or muscle or very soft tissue, you should lower the kV so that you will get good contrast to differentiate between the fat, the muscle, or even like a very soft kind of tissue and without injecting with the contrast agent. So with lower kV, you were able to get good contrast, especially on soft tissue. But when it comes to high density material like a bone or tooth, it is good to use a high kV. It's good to go with a high kV. So this is how it works. So imagine this is your material and this is the X-ray. So for this area, it has a bigger volume, and there are more X-ray that will be absorbed by this area. So the back projection, we call it back projection or the shadow, the signals that can penetrate through this object will be less. So you will see this shadow here. Okay, this is how you get it. And for a ex vivo or a MicroCT, what it do is the sample will rotate. Okay, so it will rotate 360 degree, and each time you will get the back projection, the shadow. So after collected sufficient amount of the shadow, it was submitted to the algorithm, the software itself, and it will reconstruct. You will eventually get the 3D image. So from a 3D image, you can further look at all the interior details by having these cross-sectional slices. And all this is going to be non-destructive. You do not need to sacrifice your sample. So after the whole imaging process, you will still get your sample in intact form. So you do not need to slice it for example, like for your histology work. So here is just a summary, just a preview, what kind of application you can do for your MicroCT. So you can do on insects, on coral, on leaf, even on the paper. This is the printing of an A here. You can do it on animals and so on. So the first applications that I would like to go in detail for sure that I'm going to start with dental research. And this is one of the samples that given by my user. Is a human tooth. So I guess the decaying region has been go into the root canal. That's why they have no choice but to extract it, to remove it. But the main purpose of this group of researchers, they would like to look at the reparative or the new dentin by using a 3D X-ray MicroCT. So when I do a literature search, basically there is no strong evidence or strong support or publication. Even there's very limited amount of publication that actually utilizing MicroCT to look at the reparative or the new dentin regeneration. So mainly they're using the sorry. So mainly they're using histology and they're doing H&E. So they're looking at the growth of the new cells. So to justify whether it's a new dentin. So this is a quite a new what you call that method for us to explore whether there is a reparative or a new dentin grow out of this decay tooth. So we have done just an ordinary scan. So this is something that you will get standard features that you get from a MicroCT. You will get the XYZ and you get a 3D. And from the software itself, when you move around, so when you go in and out, so you will create a different 3D. So that's the standard features. In the future, if you have a opportunity to do a demo on the real virtual demo of how the MicroCT works, you will have a feel of how it looks like. And of course, I have also compiled it into slices, so different slices. So at this cross sections, this should consider as XZ view of the tooth itself. So you can see how bad is the decaying region, and this is getting less and less. So you will see the contrast very well. Okay. And when we zoom in and we are looking at the different contrasts and we are exploring which layer are the new dentin, we find out that there are actually 5 different layers, 5 different contrast layers. So you can see one layer here, one here, one here, one which is here. This should be the similar at this area, and one here. So these 5 layers, basically you will not see on the healthy region here. So we will need to do further studies on which are the layers is indicating the considered as a new dentin regeneration. So of course I am not a clinician, so I cannot really tell which is considered as a new grow dentin layer. So this is what a MicroCT with good contrast can deliver, the data that can be delivered to out of a decaying tooth by scanning a decaying tooth. And we can also utilizing the MicroCT to characterize the tooth by looking at or measuring the porosities or even the density of the demineralized layer of the tooth. So for example, this is a mouse maxilla. So this is an overview how it looks like. So from one set of data itself, we can utilize the same set to do a lot of studies. For example, we can look at the porosities, or we can look at the demineralized, because like you see here, there is a lower density layer compared to this. So we'll consider this as the demineralized layer. So let's look at the porosity. So what we can do is we just need to select the area that we think is critical for our porosities studies. Okay, then this is what we can get, the thickness map of the pore and also the pore networks. And all this color coded here, you will expect the blue one with the thinner or thinnest, what you call that, the connectivity, the networking. And the red colors are considered the thickest. So from here, at one look, you can tell which area has a very thick network. These are the rest are very thin network. So and this is also you can get result in the Excel. So with the distribution here. So from 0.01 pore diameters up to maximum, the thickest will be about 0.06 mm of the pore diameters. With all these data like the density, the degree of porosities, the connectivity, the pore volume, and everything here. So this is all the standard features that you can get in a MicroCT. And at the same time, you can also look at the outer layer, the how what is the level of it is losing the density, or we call it a demineralization of the tooth. So we can highlight the whole region here, okay, and we can use the software to create a very nice representative image here. So the green color here are indicating the demineralized or the layer which has a lower density. And we can also convert all this green layer into a thickness map. Okay, so you can see that the red color is the thickest compared to the green and the blue color here. And again, we do have an Excel it's a distribution which is in Excel format. So we can plot the graph to look at the distribution, and we can get another group of results to indicate the demineralization of the bone. And move on to the tooth, we go into the implant. So you can see this is the implant and this is the abutment, the screw itself. So this is a titanium and it ranges like about 3 to 5 mm. Normally, it's commonly used for the implant. Please correct me if I'm wrong. So so you with this, you doesn't really require very high kV, like above 100 kV. By just having a 90 kV of MicroCT, you will get a very nice 3D of this titanium implant. So from this 3D MicroCT image, you can get the external view, and you can get the internal view as well, the cross section, how it looks like. So you can remove this layer, request the software to remove this layer so that you can see the internal structures of this abutment, of this screw itself. And you can also submit this part into the request the software to study the thickness of this abutment itself. So this is how colorful and You can look at the distribution of the thickness. Okay, so you can merge all the data together. So by using a 90 kV, you basically can see we can resolve up to 5 micron gap width between this the implant and the screw itself. So with very high resolution. And not just getting apart from getting the 3D, the structures of the implant, we can also study the bone implant interface. So how well, like let's say after we do the implant, we would like to see how well the implants and the bone itself, the bone is wrapping or is growing around the implant. So this is something that we are interested, especially for dental research. So from this image here, you can see this is green, which is the implant. This is transparent, which is the bone. And you can see there's some red color here. So the red color part are the region where there is interaction, there is contact, direct contact between the implant and the bone itself. And we can also convey this red color into percentage. So every single line or every single pixel of it, it can give you a percentage of the contact surface between the bone and the implant. And of course, we can do a animation to do the volume rendering. And for some researchers, they would also like to do simulation to calculate by using a software how well the implant is being loaded into a bone by just using simulation. So for example, here we have a load case by using different kind of forces. So you can see the red color means is actually the bone area is encountering high force from this object here, which is the implant. So by using different kind of implant, you will see how what is the force that being encountered by the tooth, by the bone itself. So this basically you do not need to really have this sample like a bone and implant, which is implant into it. What you need is you just need to provide the information. You need to scan the implant separately and the bone separately. So you submit into the software, where we call it is a final element software, and then it will do the simulation calculation. So you do not need to do the experiment. It's just a simulation test. All right. Okay. So okay, we move on to next application, which is a bone research. Okay, so for bone research, by using a MicroCT, you basically can see all the very fine structures of the trabecular, the bone trabecular. Okay. So you can see very nice volume rendering and all these very micro structures from the bone itself. And not just that. So for example, this is a cortical. And within the cortical, there's a lot of capillary, where we call it as the Hessian canals. So we can also utilize the software, which is very clever. What they can do is to do invert, like now what you can see here, the high density will be the solid. So what you can utilize the software to do is to convert it from the low density and make it solid. So when you invert it in such a way from the low density become solid, you will see there is a lot of networking here, where we call it as the Hessian canals. So all these Hessian canals can ranges like for like a 20 to 50 micron. So if you look at the next example here, this is also another cortical bone, the solid. And this is after invert the low density into solid. So what you can see here, this is the Hessian canals, all this networking here. And what you can see, all these dots here are the astrocytes, which is ranges from about 5 to 10 microns. So, and from here, we can further analyze like the volume or the number of the astrocytes by using the software. So this is how powerful the software can do a lot of analysis. So this is another example of a mouse knee. So this is the very a conventional look of a mouse knee. And we can have a closer look at this region. We can look at the trabecular thickness. Okay, so the red color is the thickest, the green and the blue is the thinnest. And from here, the trabecular itself, we can further zoom in and look at the capillary within the trabecular itself, where we call it the Haversian canals, all these networks here. We can also do bone strength characterizations. For example, for researchers that would like to see whether they, after they have implant or modify or treat the animal bones, they expecting to look at the bone regeneration or the scaffold implant, or after they have injected with some kind of mesenchymal stem cells or cartilage. So they would like to look at the before and after. So they can look at the thickness, and they can also use the final element that I have mentioned to study the strength of the bone. So you can see here, this is the distal part of the bone. This is the proximal part of the bone. And from the final element itself, you can study the red color part means it's actually encountering very high force. So if we further increase, we can use a simulation to do this as well. So when we further increase the force, this will be the area that will fracture. So that's the prediction that provided by the software itself. So you can see this area, which is high porosities. So definitely you will see the cortical layers here is in red color, which also means that these are the patients, these are the subject that will encounter fast bone fractures if there is this amount of force being applied to the bone. So this is something that we can use final element to characterize, to do the calculation. Okay, so next is general biomedical research. So we can do it on a brain. We can look at the brain. So by using a MicroCT, we can resolve the smallest vascular structures as small as 1.4 micron. So further zoom in. Okay, we can also study the thickness. Okay, that's the standard features. So this is a nice images of a mouse brain, and this is a brain tumor of a mouse. But of course, this one has been injected or treated with a contrast agent. Okay. So we can also look at lung. And for MicroCT, it can be divided into ex vivo, and it can be there is setup that specifically designed for in vivo. So for in vivo types of design, which I didn't cover today. So for just for sharing, so for in vivo kind of design, they have their software to calculate light, because when you're trying to try to capture the image from a live animal and they are breathing, so you can see that the lung is expanding, shrinking, expanding, shrinking. So the software will have the calculation, will have the baseline, the threshold, up and down, and they will capture at the standard time, standard rhythms, so that it can all compile together and give you the image of the lung, even though in a live animal. So same goes to a cardiac heartbeat. So that's for the in vivo MicroCT. Okay, so this is a cardiovascular system with contrast agent, and this is a very fine structures of the blood, the vascular system, the blood capillaries, okay, of a rat. And this one is another example. We can look at the tablet. So for this case, they actually find out that there is some cracks happen in this tablet production. It's actually from a pharmaceutical company. So they will, first of all, by using a X-ray CT, MicroCT, you can study the crack without need to cut or destroy the tablet. And And by using the software, the slices, so you can easily identify the area with the crack here. And at the same time, you will see there is different density. So basically, you get one intensity. This is another very bright spots, and this is gray, and this is another intensity, different levels of the intensity. So all this might have indicated different materials in the tablet itself. So these are the things that we can capture by the software and do further analysis. So for this one, basically it's focusing on the crack. Where are the regions with pores or cracks? So you can see at the middle, this is where the cracks are located. Okay, so you can get the distribution of the crack. And this different colors, the green, red, and the yellow is the crack. So you can see there is indicating a different compounds based on the intensity that we obtain from the slices, MicroCT slices. So from here, we can calculate the volume, okay, based on the density. And material research, so we can do scaffold, titanium, no problem. We can use it on battery. We can use it to do aerosol can. So for this, in industry, it will be useful for failure analysis because they already assembly the whole thing and end up the aerosol can just malfunction. It doesn't work well. So what they can do is just throw into the X-ray MicroCT here, and they would like to see which are the area that cause the default, cause the malfunction. So this is also useful in industry. And also the printed circuit board. So this is more for the material and the semiconductor industry. And we can also use MicroCT for different kind of geological research. So like a stone, this is a frozen soil and ice. This is a bricks. So earlier I have students that I assist him to do because he's from construction, from a cost of doing utilizing different materials, different combination, and he would like to check on the density and also the how compact is it. So we actually get the material and then we do MicroCT scanning, and we come up with a report to tell like how compact is this. And by using final element, we do simulation of how strong is this compound after it has all mixed together for a construction purpose. Okay, so we can also look at the crack, study the crack without destroying the rock. And we can also study the rock inclusions. So for oil and gas industry, of course, oil and gas industry, normally they were utilizing a huge setup that whereby they can bring a portable CT scan to the location of interest. So they can utilizing the intelligence from the CT scan, and they look at the inclusion in the rock itself. What kind of whether there is suspicious inclusions within that giant rocks or area. And we can also use it a lot of researchers, especially in Switzerland, they are looking at the fossils. So this is the fossils of the items. So you can see is a group of the items. So we can further zoom in and study a single microfossils by having the details of about 600 nanometers. So you can see all the tiny features of these microfossils. And this one is another one. This, if it's not mistaken, is a small what do you call that? I forgot. There's a name for this animal. Sorry, I cannot recall. Okay, so they can do it on fossil. And the biggest that we have scanned is fox, which is a fossil, and a fox. So you can imagine the size of a fox is quite huge. So we do have MicroCT whereby it allows a big object to be loaded into the MicroCT. So without destroying the fossil itself, we can identify what kind of animals is embedded within the stone, within the fossil itself. Okay, fibers. So we have done it on a face mask. So you can see clearly the 3 layers of the mask. Okay, and you can look at the thickness of the fibers, every single strand of fibers. So you can calculate all of them. And this is a climbing rope. So you can see the structures is very complicated. Okay. And especially after you zoom in, it's very complicated. So we have to understand that the concept of rotating the samples and we capturing the shadow. So after we get sufficient enough of the rotation and the back projection, the shadow, and we able to reconstruct all these complicated features into what you are seeing now. So it's a very intelligent software behind this MicroCT. Okay. So this one is a cocoon. So with the pupa inside there. So this little guy here. So we can view the interior part of this cocoon, which is the pupa here, of the silk pupa here, without need to destroy the cocoon. And this is the single silk fiber. So this is a fiber. And we can even look at whether there is any pore within one single strand of this fiber. And we, of course, we can also look at the overall thickness of this fiber. And there is also people looking at food. So this is some of the commonly seen food like black pepper, clove, and we can also do it on mayonnaise, parmesan, the cheese. And there is factories that producing twiglets that actually want to study how crunchy, like when it comes to this amount of pores, how does it contribute to the crunchiness? So these are all the studies that they can use. One of the samples that I have came across is the bread. So this group of researchers, they would like to see what kind of bread after being chewed for how many times, and the changes on the softness of the bread. So their main purpose of this research is to look at what kind of bread will be suitable for patient, which requires minimal amount of chewing, or how well it can digest after they are applying some acid to mimic the gastric, the acid, and how well it can be digested, how fast it can be digested. So these are very interesting research that we utilizes MicroCT to do all this mimicking to enrich to increase the impact of our research. So this is also a mushroom, an image of a mushroom. So you can color them and make it looks like a real drawing of a mushroom. And this is a dry raspberries. So you can look at the interior structures of a dried raspberry. And insects, okay, and entomology. So this is a butterfly. So you can see all these compound eyes, the details of the compound eyes. Okay. So after you segment them, so you can see all this comprises of the ommatidia. Okay. And this is a fly. So you can get all these details, the compound eyes, and all these hairy structures. And also from this bumblebee, which is very fine structures of the hair, very soft structure of the hair, which is able to be captured by the MicroCT. So it shows how powerful it is, the software of this MicroCT. Okay, so this would be my last pictures. So this is from a bee larvae, so we can see all the internal organ of a larvae here, bee larvae here, and also wasps. And that's all I have collected today. So feel free to ask anything. I'm more than happy to share more information if I have now. Okay, thank you.
Thank you, Dr. FT, for
Thank
the
you.
amazing presentations. I see from the participants we have quite wide range of participants. We
Oh,
have
okay, that's good.
practicing dentists. We have even from UAE Hospital, Dr.
Mm,
Ain, from Kuliah of Allied Health. Okay, so that's amazing. And also from Ministry of Health, Dental, and yeah.
mm,
So. Uh, just to give some insight from our side, from
mm,
dental radiology, we have our CBCT that is currently can do up to 50 micron. And our kV is around 90 to the maximum one now is 120 kilovolt, but the MA is only up to 15 MA. So we cannot get the even you scan at 50 with MicroCT, we cannot get the same quality as our CBCT now lah. Okay, and I noticed that even for your implant image, I can see that there's no beam hardening artifact from the implant that you can. Yeah, so that is amazing. We can see clearly the groove of the screws, even for uh, the screws inside. So that
yes.
is very amazing because definitely we cannot see it from our imaging modality here.
Uh, Mainly because
Okay,
the way they design the algorithm, they write the algorithm, and they try to remove all this artifact. Mm.
so that's amazing.
Sure.
I have few questions, but let me read from the chat box first.
Sure.
Okay, so we have Dr. Samiullah. He's asking, can we use this technique to see and research of Harvesian system and Volkmann's canal?
Yes, you can. You can.
Yeah,
Mm.
you can. The answer is can.
Definitely can. So like this. So the 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 main thing here is, as long as you have sufficient a micro-CT that sufficiently resolve the thickness of the Havitian canals and the Walkman's canal, and you can, for the software part, is easily you can request the software to, like, if you can see here, uh okay, you can see there are red dots, which are the cells, and this one is the canals is here. So as long as you can identify which density, whether it's high or low, if you know that the density of the cells ranges from, let's say, 1 to 10, and then the Havitian canals, the density of the Havitian canals ranges from 20 to maybe 50. And the bone will be definitely like few hundreds. So you just need to tell the software that, okay, I want to focus like 20 to 50. So the software will highlight, will contour all these features that falls within the range, within the density range, and you get this beautiful uh, layout. Yeah. After that, yes.
Okay.
And after you have this layout, you can continue the studies by doing all the volumetric calculations, the connectivity and things like that. Yeah.
Okay.
Mm.
I hope that answers Dr. Samiullah.
Yep.
Okay, so you mentioned about softwares,
Mm.
how it's not only about the MicroCT itself, but also the software to manipulate the images. Okay,
Mm.
so does the software comes together with the
Definitely.
MicroCT hardware, or we have to find our own software?
I'm not sure about other brand, but for Scanco, they spend a lot of times on creating their own software, their own scripts. Yeah, so it's definitely come together with as one set, one package. Yeah, that's why when you pay the that amount of money, it's not just for the hardware. It's actually for all the small things that hidden behind. Yeah.
Okay.
Mm.
So it means that Scanco MicroCT is a good system because it comes together not just the hardware but also with the software. Okay. So before I proceed with my next question, I would like to open from the members of the floor if you have any questions to our speaker today.
Uh,
Rosanna.
yeah, good morning, Lim, FT, Dr. FT Lim.
Yeah. Good morning, Prof.
Okay, I just would like to ask a few questions based on your presentation.
Yes.
Number one, uh, with regards to dental research, uh, I just would like to, I know you can see all these new dentine regenerative studies, but we do have stem cell studies at our kuliah, our school.
Mm,
Stem cells is basically promote growth of other parts of the tooth tissue,
mm,
promote the enamels, the bone of the teeth.
yes.
So do you have any experience using Stanco MicroCT looking into stem cells regeneration?
Uh, Frankly, no. But Prof, if you have one, we are happy to try it out. Because
Okay.
we sometimes it's quite difficult for us to get the good samples for our own trial. So if you have we can arrange, and if possible, I'm not sure whether does it has to be in culture medium, or can it be dry dry
That is,
form?
yeah, that is basically secondary.
Yeah.
It's a more on in vivo or animal study that we can
Mm,
section that
mm,
area, or we
mm,
can do a teeth sectioning, and we can scan the teeth,
yes.
and we can see the if there is any new tissues generated based on your micro CT data. So the densities, whatever. So I think
Mm,
the code color coding of new bone. So that's what I was just in case we can do that. I think we can look into that parameters.
yes, I think we
Okay.
can try,
Yeah. Right.
because
Okay.
if there is a density difference, especially from the young
Yeah.
cells
Yeah.
to the mature cells, we should able to
Okay.
identify them out.
All right. Okay.
Yes.
All right. I have many questions, so I just briefly. Number two,
Uh,
you did mention about bone density. May I know your bone density is based on is it a gray values or Hounsfield value or any values? Can you tell me
yeah,
what
both of
values?
them. Both of them. Gray values and also a HA,
Oh, I
CCM.
see.
Yes.
All right, all right.
Mm-mm.
Or you use the same principle as CT.
Yes.
All right.
Yes.
Because I can see when you look into bone density, a new bone, it can there's around 197 micro HA. That means HA is Hounsfield value, is it per cube?
Yes.
Uh,
Correct.
all right. Okay, okay.
Mm, mm. Because we
Uh,
do have our own
okay.
calibration.
All right. Okay. All right.
Yeah.
So okay, it's a good study that we can see new bone formation and can see the
Mm,
density.
yeah.
All right. Next, you did mention about the osteo. Actually, the word we use is osteo integration, where the implant married with the
Ah.
bone. That
Okay.
is called osteo integration, where the implant is stable.
Yeah.
You have that osteo integration with regards to color coding.
Mm,
But it is also good if you mention about the values, the density, because we would like to see the density of the implant and the density of the bone, whether it should be different, but that shows there's some growth going on alongside the abutment of the implant.
yes.
Uh, yeah, that's what I said. I think we can see more on integration. Your final element analysis, simulation. It can be applied to any software like NCs or any other FEA software? Is
I
it
think yes.
compatible?
Yes.
Is it
Yes.
compatible?
Yes, 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 it's compatible. It's just that
Mhm.
for this one, the ScanCore itself do have their own built-in final element software. So if you have the built-in means is
Okay.
less hassle as you have to export out
Yeah.
the relevant format. But of course, it is still compatible to the other types of final element, just that you have to export out the format, which is can be imported into the software, acceptable by the other software. Yeah.
Oh, all right. Okay, fine. So you have an in-house FEA analysis. I mean, inside the software,
Yep.
inside the
Yep.
yeah. Okay.
Yep.
All right.
Mm.
With regards to changes of pre and post, I mean that when you want to see pre treatment, pre-research. I mean, then after that you see what happened after you put something post. You have two images. So
Yes.
these two images, new and old, old and new.
Mm.
I mean to see bone trabeculae or to see
Mm.
bone geometry or the Harvesian systems, all these things. So
Mm.
do the data can compare from your data acquisition data that they can compare this both pre and op inside your
Yes.
software?
Yes, in ScanCode they do have a script. They have a script that what they call it is registration. Means
Okay.
like one is
Mhm.
before, one is after.
Mhm.
So you have to scan the same
Mhm.
object before and after. Then the software will align them, will stack them together,
Yep.
and then they will compare either the whether there is any growth, increase of the size, volume, or changes at the densities and things like that. Yeah.
All right.
So
Okay.
this,
But just one thing, the FOV or focus of the view that the maximum
mm,
when you say about the scanning fox fossil, all these things,
yep.
it can include all those structures, a skeleton of the animal. What's
Mhm,
the
mhm.
maximum size do you have for your FOV?
Okay. For Skenko, we have three different range. One is for
Okay.
ex vivo, one is for in vivo, one is for human.
The maximum.
So
Uh-huh.
yeah, so for the human one can basically load up to uh about 1 feet
1 feet.
feet of
Oh, that.
diameter.
Oh, oh,
Yes. Yeah.
1 feet, 12 inches. Is
Feet,
it right?
30 cm.
Or
30
cm?
cm of diameter. And length basically is unlimited length. So because it's come with like it's quite similar like the clinical type of CT scan. So length is not an issue, it's the diameter. So the diameter is about 1 feet. And the resolution for this clinical MicroCT is the best can go down to 24 micron. Yeah, that's the best resolution.
Okay.
So yeah.
Yeah, I think I'm not sure about the higher in the CT scan, the higher the resolution, the acquisition is better. You can see more minute structures. But here in MicroCT, the resolution is lower. Is it? From my understanding, is it low compared to CT? When you say that, because
When I say
the the
sorry.
resolution. How do you?
Oh,
Uh,
because for ex
yeah.
vivo, okay.
Uh-huh.
We have to depends to two factors. One is the time it spends to scan one
Uh-huh.
sample.
Yeah.
So
Yeah.
for in vivo and also clinical, because we want to minimize the radiation, so we need to have very fast scanning. So with that,
Uh,
we definitely need to compensate with the resolution. So we need to give up,
mm,
like we need to sacrifice the resolution. But for ex vivo, we have no concern about the radiation, and
mm,
it's going to be, fully shield the
mm,
whole scanner. So we do not afraid of, the radiation being leaked out or things like that. So we can
mm,
scan with a reasonable amount of time, and with the ex vivo type of the working principles, we can get a very good resolution, even up to submicron
mm.
level. The best that we can
Okay.
go is about
Mm.
0.5 micron of resolution.
Okay. Like lastly, I think it's good. Is a potential. I think collaborations of further strengthening our research. I think we do have a very big societies in Malaysia. One is Dental Material Society. headed by by Dr. Das. From University of Science and others from university, our university, and also we have a biomaterial society. They're all doing some research based on the materials and dental materials. So I think it's good that we can have MicroCTs to further analyze the data in terms of the clinical application later
Yes.
on. So I think it's good that we can further discuss. Thank you very much, Dr. FT Lim. Thank you very much.
Prof. Thank you, Prof.
Yeah.
Okay, we have one more from Dr. Ain. I think she's the radiation protection officer from our hospital. She's asking, in terms of safety, does it require specific shielding as common medical CT that we have in our faculty or in our hospital?
Okay, as I mentioned earlier, we have three types: ex vivo, in vivo for animal, and for patient clinical. So for the ex vivo and in vivo, we do not need the shield because it's fully covered, fully shield. So we can give guarantee that the minimum amount of radiation that you can detect it like 5 cm away from the scanner itself. But for extreme CT, for the clinical one, we call it extreme CT. So the clinical one, because it's something like the hospital types of CT scan. So there will be a certain amount of exposure. But of course, when we design the whole system, we actually ensure that the exposure in 1 minute, we are calculating it as 550 micron sievert. So if as what I experience is if the installation is in clinics like radiology department or in a hospital, they will still require shielding. But if it's in for research use, I don't think, because for overseas like European country, they does not require this shielding. So I am not sure like what is the rules and regulations in um IUM in your department. So it's quite dependent to different rules of the university.
I think to add on the questions, my experience when I was in USM, Kubang
Mm,
Krian, we do have a
mm,
Scanco Micro City, the standing one, the tall one a little bit. That was basically located in a room, like a lab. And I think in terms of safety, we basically informed our safety radiation officers or the Kementerian Kesihatan.
mm,
However, because the machine is being the machine is being the X-ray machine is being manufactured in terms
mm,
that they have already the shielding or materials, everything is inside there, so it doesn't harm people outside, so it's safe. So that's why
mm.
we is located in a lab where people are working, and something that in the
Yes.
public area.
Yes.
Yeah.
Okay,
Thank you,
And
interesting.
Prof.
also, I think my experience when I was in MINT, Malaysia Nuclear Technology, they have a scan, micro CT. It's also, in a located in a room in the lab, something like that. Yep.
Okay. And one last question. For aspiring researchers that yeah, when we look at your presentation, we have some sparks of idea, or I want to do microcity research too.
Hmm.
Do we have any place where we can send our samples to run
Mm,
microcity?
okay. In Malaysia, currently, there are few proposal going on. So I think not this year, maybe hopefully by next year. Okay, there are few proposals going on. Thailand, they are quite a lot of installations. If you would like to form like a collaboration with them, I am happy to link between the head of department and researchers. and then you can send sample to their lab for their services or even collaborations. And of course, if you do not want to collaborate, you want to ask for services, yeah, you can you can send directly to Scanco Medical Switzerland. So they accept sample as well. Yeah.
Okay,
Mm.
thank you. So at least
Dr. Bat,
yeah.
can I add? I just would like to know in Thailand, what research or I mean studies they are doing. I mean, most of them are they doing dental or biomaterial?
Dental.
Dental.
One of them is biomaterial, but
All right.
it's still under dentistry, but he's looking at the zirconia.
All right. Okay. Fine. That's
Ceramics,
good.
yes.
That's good. Which university is that?
Konkan University.
Oh, Konkan University. All right. Still,
Prof knows.
Bangkok. Yeah. I've been to near. I've been to Chula and Mahidol, but Konkan is quite near to Bangkok. Right.
Yeah, 1 hour flight from Bangkok. Yes. But
Yeah.
Mahito and Chulalongkorn also have MicroCT. Yes, they have
All
more than
right.
one.
Okay. All right. Okay.
Yeah.
Good. Thank you.
Okay. I think that's all. If anything from members of the floor, if no, then we have request from our head of research to take a group photo. So maybe Dr. Lim can stop sharing. We will everyone to switch on your camera.
Stop sharing. Okay.
Okay, everyone can wait for a while. Okay, okay, everyone. Okay, ya. Dr. Syafiq ke yang ambil gambar ke saya?
Boleh.
Dr. Syafiq. Okay, Dr. Syafiq yang boleh ambil gambar eh. Okay, everyone smile. Okay. Okay, next page. Okay. Okay, if nothing else, then if there's any questions from members of the floor later on, just let us know. We will connect to Dr. FT for further collaboration and samples from the members. And thank you everyone for joining, and thank you Dr. Lim for sharing.
Thank
And
you.
hope
Thank you for
everyone have a good day.
organizing.
Thank you.
Right.
Good to know
Thank
you
you,
all.
Dr.
Thank
FT. Thank you.
Thank you, Dr.
Bye-bye.
Azim. Bye. Bye. Have a good day.